So let me share my screen. Welcome everybody. There is a small problem right now. We are able to, only add up to 100 participants, and we are happy to see that, there are so many other people who are waiting in the queue. But I'll figure it out, how to manage that. We actually have up to 500 people we can add, but there is some technical problem right now we are facing. So sorry for that. Anyway, we are going to record this, and we will upload it on our YouTube channel so that it will be available for you to watch later. So today we have a distinguished guest for the expert talk. Okay, Dr. Jeff Franklin, the director of CFD at Airflow Sciences, USA. And before handing over to Jeff, I'll give you a brief intro about Flow Thermal Lab. As a company, I'll take just 1 or 2 minutes to introduce about ourselves. And I'm Sandeep. I am the founder of Flow Thermal Lab. And what we are doing basically, we are an online platform. We help in online education and also consultancy services in the for the industry, especially in Europe and in the Middle East. And we are happy to share you that we are now going to be we are going to celebrate our 3rd anniversary in a couple of days. This is our office where we are. We are incubated at the University of Nottingham at the Business Park, along with many other startups. And we are also in India and in the UK as a registered company. And about where are our students, right? So I have thousands of students now on our online platform learning CFD, programming, and many other stuff related to scientific computing. And we are happy to share that we have students from 67 countries all around the world. So it's a very, very interesting numbers for us as well. And yeah, I mean, you can learn CFD or scientific computing, like the programming, CFD tools, fundamentals, everything on the platform. Learn at your pace, and also there are live programs where you can participate in the live sessions, in workshops and things like that, specialized workshops. And there are also you can explore different courses there. And there is also our flagship program, the mentorship program, which runs for 6 months, which got several stages, and also helping in the placement assistance. So this is something which you can also think about if you are interested in. And if you are from industry and are interested in consultancy work, you can also approach us. We are specialized in CFD, but we also do help in FEM and coding, etc. So that's a very brief intro about Flow Thermal Lab. So I don't want to take more time about this, and let me introduce Dr. Jeff here, our expert for today. So Dr. Jeff Franklin, he got PhD in mechanical engineering and MS in chemical engineering from Wayne State University, USA. And he's the original author and architect of the commercial CFD tool, Azure. And he built it from the scratch as and he built a very interesting, very very brilliant software, I would say. He's an expert in C and C++, numerical analysis and programming. And also he got decades of experience, applied CFD as well on the real application side as well, in the field of fluid mechanics, heat transfer, mass transfer, combustion, and you name the field, he's there. And so today, our topic is all about CFD post-processing and the technical aspects of it. Like how you, because the CFD post-processing is something very, very important as an engineer. This is where you do everything, all the CFD analysis, I mean the simulation, but at the end you need to post-process your data. You need to analyze your data. This is where you are an engineer, right? And you're going to apply it for a product development or whatever you're going to do. So today's talk is all about CFD post processing, and in that very specific topic about the surface integral of collocated CFD data. So I hand over to you, Dr. Jeff, and thank you very much for joining this session.
Great. Well, thanks. I'm assuming you can hear me?
Yes.
Okay, I'm going to share my screen here.
Yeah.
Can you see it?
Yeah.
Is it in full screen mode?
No, not yet.
Interesting.
You can try slide on the top. I think you tried earlier slideshow.
Yeah, it's not going there. Let me see here. I'm going to stop sharing.
Yeah.
And try this again. Let's see if this works again. It'd be nice to get it. It was just full screen a minute ago.
Yeah.
Of course, it doesn't work now. Just 1 second here. I'm going to get out and get back in here. Maybe that
Yeah,
will help.
sure. Yeah.
Hmm.
Mm,
Yeah, why is?
it was working. Maybe.
Yeah, that's what. Yeah, that's just. Let me
Yeah.
try a different way of doing it here.
Yeah.
I'm gonna share all my screen here. And
Yeah.
can
I
you
think it is.
can you see it now?
Yes.
And just in full screen mode?
Yes. Yes. It is
Oh,
working.
great. Okay.
Brilliant.
Great. So like this is the intro slide, and he's thanks for the introduction. It's actually an honor to be here. I'm glad to see so many people interested in this very specific topic. As Sandeep said, I've spent a lot of time in both the field of developing a CFD tool, which is Azor. I developed a numerical engine for that, and I did that decades ago at the time when there weren't a lot of post-processing tools available. So I also spent a fair chunk of time putting together a post-processor so I could actually look at the results visually. But as well as I work for Airflow Sciences, which is, a consulting company that does jobs, for all manner of CFD. We apply CFD techniques to solve customers' problems. And I've been doing that for decades as well. And so I've spent a lot of time, I understand the ins and outs of the numerics and what the solver is doing and what the data is available to look at. And I'm very keen on making sure that the post-processing and the information that you gather and present to customers or whoever you are presenting your CFD results are kind of faithful to all of the information that the solver has provided. And today I'd like to kind of dig into a lot of these are going to be some very fine details about the specifics, because sometimes if you use a post-processing tool and you mine that CFD data, especially if you look at it very carefully, you can kind of get conflicting information, especially if you're looking at very close results and comparing design simulations that have very small differences. And you should never really get that from a CFD tool. It really comes down to how you post-process the data from the CFD tool. And I'm going to discuss some of those inconsistencies that if you encounter those things, you'll maybe have a better understanding of what they are and why they may occur. And then hopefully with that kind of, perspective on that, it'll arm you with ways of dealing with it and understanding what's going on rather than like being left with like, well, why am I getting inconsistent results here when I really shouldn't? Um, it's kind of the goal here. I wanted to go through. Oh, is it not now? Oh, okay, there we go. So the general post-processing goals from me, from my perspective, is basically I'm going to really focus on collocated CFD solution algorithms, which are pretty widely used, especially for industrial applications. The like, Azure uses them, the likes of OpenFOAM, ANSYS Fluent, STAR, they all use this same general technique. So these algorithms, we worked very hard to give us these, solutions that are faithful to the conservation equations that we're solving. And what we want to do is we want to use post-processing methods that also mine the data in such a way that the data generated by the solver is honored when we post-process it. Like if we post-process something and we expect conservation of mass from the solver, we should also expect conservation of mass from our post-processing tool as well. And it shouldn't be just close, it should be spot on, in my opinion. Otherwise, you get ambiguity in the things that you might be post-processing. And so that's the kinds of things that, the goal that I have in terms of post-processing things. So today I'd like to really just kind of dig in. I kind of have an overview of what's going on here. I want to make sure everybody's kind of on the same page with what a control volume is and how the control volumes are connected to CFD solutions. And then I thought maybe we'd go, because it really comes down to CFD tools, it's the velocity field. That you got to have that first before anything else. And so we're going to kind of go do a little look at history a little bit about how people solve the velocity equation. You need to solve the velocity equation, which is intimately connected to the conservation equation, because those kind of are very closely connected with one another. And we're going to do a little history lesson about how people stored data, how it evolved to this collocated mesh thing that is commonly used now. And then once we kind of understand that, then we're going to go over like, what is a surface integral of this data? What do we really expect to get from it? How does it relate to that data? And then I'm going to dive into some very specific examples that highlight some of the problems you might have if you don't do these integration methods correctly. And so that's this T-junction example, and we'll look at a simple flow of viscous flow through a slot. We'll look at a temperature mixing problem, which is a little bit more complex problem about surface integrals, and then we'll kind of summarize all of the findings here at the very end. So that's kind of a summary of where I hope to go here in this discussion. So the first thing is what is a control volume? And for us and for this discussion, I'm really going to kind of focus really on steady state. That's easier to think about. If it's not steady, then some conservation inside a control volume gets a little bit trickier. But for right now, let's just say things are rolling and it's steady state. And so now we have a control volume, and we always set that, as engineers or physicists, we set up problems and we like to kind of fix the space that we are going to analyze, and it's a control volume. It's a fixed space, and over on the right-hand side, you can kind of see we've picked the space that represents what we're going to look at. And then basically our fluid kind of passes through that space. And the space is usually kind of collected together with these parallel faces, these kind of linear faces. And the center of it, that little black dot, that's kind of what we say is the average value for what is inside our control volume. And then these little blue dots are kind of the centroid of each one of the faces. And we kind of average out the data that goes in and out of each one of these faces. And then we have the little arrow here that kind of says the directionality, because you kind of have to pick a directionality for your conventions of things going in and out of this control volume. And so this kind of characterizes a control volume. It's basically a bunch of surfaces that enclose a space. And so once we have kind of put together this space here, then we can conserve our various quantities. And as typical, we have conservation of momentum, for instance, that gives us our velocity field. We have conservation of mass. That gives us our conservation of what comes in and out of each one of these, energy, and there are other things too that could be also conserved depending on the problem that you're solving. So that's the gist of what a control volume is for us, and we're going to kind of extend that over. So now in a CFD simulation, what we really have is we have a whole bunch of these control volumes, and each one of these control volumes in themselves, they control, the mass and momentum and everything. But the good thing about these control volume methods is that everything is conserved locally in one of these, but also collectively, they also control, they conserve all of the quantities that we're interested in. These are our engineering quantities. These are the things that we are wanting to extract, or these represent what we want to solve or use to do our engineering analysis with our CFD tools. So these are our control volumes, but what do they really mean from a integration standpoint? So when we do a surface integral, now we have, say for instance, here we have two collections of cells. We have a group of cells up above here that are one color and a group below. And we have basically a kind of a collection of faces that are shared between these. And that's where you might want to do a surface integral. And that surface integral, you would kind of expect it to also follow the same rules, that if all of the mass passes, collectively from this group of cells, it has to go into these. And so we would expect any type of surface integration technique we choose along that line to also conserve mass for each one of those control volumes. That's really our goal, and that's what we want to get out of these surface integrals. If we find the average mass flow rate through this surface, it certainly must, individually, as you add up each one of these, be conservative. But it's a little tricky here for the control volume technique, because usually the data for each one of our CFD tools is stored at the center of each one of these cells. That's the collocated location. So this little black dot right here is kind of nominally where the data is for our CFD simulation. And over here, CFD simulations typically don't store data at the faces. And so you're left with interpolation methods to kind of approximate what these should be. And that's where the ambiguity sometimes may step in, is how do you interpolate that, especially when you're using complex shapes like we do these days with unstructured meshes, polyhedral meshes, and it's not clear. Like if you wanted to get a value for this face right here at that blue dot, depending on what interpolation method, you might want to choose between this point and simply use linear interpolation and say that's close enough. Or perhaps you would want to use this point over here and include that and use 3 points. Or maybe you would want to include 4 and use these over here and that one. So depending on the interpolation choices you choose, you could get slightly different answers. And those are the types of things that we're going to talk about, is how do you do that? How do you look at these things and try to get as reliable of data that closely represents the true conservation equations that our solver has worked so hard to find. So to start this off, let's look at the original control volumes methods used for solving the coupled momentum and continuity equation, because that was tricky to do, and we're talking decades ago. And the original method back in 1965 that people found to solve the conservation of momentum and continuity together was this staggered mesh. And that worked pretty well, and it was very widely used for solving these. The primary variables were stored at, convenient locations for interpolation. The mesh structure was very regular. It was basically rows and columns of square cells. And it most importantly, it overcame this like pressure checkerboarding problem that plagued many numerical analysis people back in 1965 that made it difficult to get a coupled solution between the continuity and momentum equation. And also this had this linear system because it had a structured manner in terms of rows and columns, which we'll look at in a moment here. It led to a very nicely structured linear system so that you could solve things. And you can imagine back in 1965, there weren't a lot of compute resources available. So they were solving things that we can do on our calculators in a blink of an eye back then. But so let's just look at this original staggered mesh concept and what they found worked well for them. And so what the staggered mesh was, is they used essentially for 2D, they used 3 mesh topologies to solve the equations in different locations. So on the left-hand side, they chose, this is the primary mesh structure right here, where here this blue area is kind of the cell that I would like to talk about here. And that's where the pressure was conserved. And so the pressure is stored right here at this cell, and right here on this face, this face, and this face, and this face, that's where continuity was conserved as it went through here. But how do you represent the velocities on those faces? That was always the tricky part. And so what they chose to do is they said, well, we can't really solve the momentum right here at this location as well, because that has numerical problems. And so we're looking for a way to do that. And what they found is like, well, we're going to choose a different control volume that is closely related to the original mesh structure right over here. And for the X momentum control volume, they chose to stagger it over. And you'll notice right here, these red lines show where the control volume for the X momentum equation is staggered over there. And you'll notice that the centroid of this staggered cell, then the velocity for the X momentum equation, it's actually pretty close to the face where we want to conserve momentum or conserve mass right there. And so that was kind of very convenient. So you have the momentum here in this cell, and then you have the Nix staggered cell on the right over here, where the momentum is conserved over here. So now you have the velocity in this staggered arrangement where the momentum is conserved right here on this location, but it, nominally speaking, it's right on the face here. So we also have conservation of mass. So that was very convenient for them. And likewise, you can do something very similar for the Y momentum equation when you're going up and down, when you stagger it up in the up and down direction, where we can kind of characterize the mass as it passes through the bottom and the top of this cell. And so this worked quite well, and it allows you to get a solution to both the continuity equation and the momentum equation at the same time. So that's great. However, it requires some interpolation here. So let's just look quickly right over here. So you'll notice here that the pressure for solving the momentum equation is also right on the faces from here. So we can use that to solve the momentum equation. So that works really well. But in order to get, we're going to have to use interpolation to kind of have the conservation, the mass coming in and out, the momentum coming in and out of each one of these control volumes. So we do have to use some interpolation techniques. And they're relatively simple because of the kind of the linear fashion of this mesh structure. We can use linear interpolation or bilinear if it's a 3D problem. So the interpolation methods are fairly straightforward. So that allows us to solve, and obtain all of the values that we need in order to solve the momentum equation. So for the continuity equation and the pressure equation, the pressure equation, I think, is kind of an interesting field because when we solve the pressure is really not really a conserved quantity, it's a force. And many times the pressure is kind of a consequence. It is a measure of the changes in the momentum here. And so that's what we really do, and the changes in the momentum, and then we kind of use the continuity equation to kind of close all of those changes together as typically the way the pressure equation is solved with the pressure correction methods here. And so that's why it's conserved right here. The velocity field, as I was saying before, the velocity field is known on control volume faces. No interpolation methods are used, but not exactly. Some depending on how people might implement it, they may try to account. You'll notice if the mesh is not uniform, you'll notice right over here, it's not exactly on the face. So you may try to incorporate a little bit of interpolation method in there to improve it. But generally speaking, when these methods are used, they're saying it's close enough for what we're trying to do. So anyway, in these staggered arrangements, the velocity is kind of scattered around here, but the energy equation and turbulence quantities or mass fraction fields, those are typically stored right at the center of the cell. So that was kind of the original method of how to store the momentum and get a solution of both the momentum and the continuity equation that didn't really have these numerical problems. And I know I'm glossing over all the math here, but I'm just trying to get at the gist of some of the problems that people were trying to overcome, and the gist of how they did that by creating all these different mesh structures to solve the momentum equation in a slightly different space than the continuity equation. So, but what are some of the disadvantages of this? And one of them, very obviously, is that, you're pretty limited in the types of geometries you can solve back with these structured mesh structures. So that was really not desirable. The other thing that is kind of tricky about that is the conservation of momentum is not really fully defined at one geometric location. Because of the staggered nature of the x momentum equation, it's conserved at one geometric location, and the y momentum is conserved at another geometric location, and then the pressure is actually at a third geometric location. So you don't really have a fully defined momentum at any specific point in space. You kind of have these interpolation errors that are scattered throughout your mesh topology, but you never really have a precise representation of conservation of momentum and conservation of mass, both at the same location. So in general, we have these overlapping meshes that kind of introduce a fair chunk of inconsistencies that are maybe sometimes viewed as, these are our approximation errors. But, can we do better is kind of the thought here. And so we moved to the collocated meshes here, and those started in, the 1985, it's very commonly referred to as this Rhee and Chow term, where let's try to store everything at the same location. And that would be much more convenient for us. And if we do that, then that kind of opens the floodgates so that we can use a much different mesh structure. Because if you wanted to use a staggered mesh structure on something more complex, hopefully you can see that would be a bookkeeping nightmare in terms of putting everything together and keeping track of that from a programming standpoint. So one cell-centered velocity field that conserves momentum, but what happens here when you do the conservation of mass, they still had this numerical problem of storing them at the same location. And the way they kind of got around that is they split the velocity, rather than scattering the velocity field of the conservation of mass and conservation of momentum across different mesh structures. They decided, well, you know what we're going to do is we're going to store a conservation of momentum at the center of each cell, but we're also going to store a second pseudo velocity field at the face of each one of our cells. And this is basically a very complex representation of conservation of mass at each face of the mesh structure that is interpolated based on the neighbor cell values, as well as pressure gradients and the general momentum that is in that cell if there happens to be a strong momentum terminator. So it actually, there's a bunch of math that's done there in order to get this value there that is nominally the same. But it's not just a straight linear interpolation. It's much more complex to kind of overcome these numerical problems. So, but this does now have the advantage that it gives us the precise representation of the fluid momentum at each cell centroid, which that is kind of very desirable. And it also has the other desirable capability that it gives us also a very precise representation of conservation of mass at each face in our model. And that is important as well, especially if we start doing surface integrals and the likes of that. We want to be able to have precise numbers as well as, you know, from the numerical side. And these methods are now used very widely. Azor uses it, of course, ANSYS Fluent, Star CCM, OpenFOAM, all of these, these tools now use, you know, some version of these methods. But the disadvantages of this is it really, it significantly increases the complexity of the coupling algorithm between the momentum and continuity because of these interpolation methods here. And getting a stable solution, getting a solution that runs stably, especially when you start throwing in the complexity and the mesh quality issues that can now surface because of the unstructured and polyhedral mesh topologies that we use these days. But and the last thing it does is it also now makes it a little bit trickier for post-processing, which is kind of the topic that we're going to talk about today, because now our velocity field is two velocity fields. One of them stored at the center of the cell, and the other one is stored on the faces. And how do we deal with looking? I mean, certainly if you're post-processing and you're looking at filled contours, that is less of an issue. If you're just kind of qualitatively looking at all of the your simulation results, these small details are really, you know, not particularly important to you. However, if you're using surface integrals and gathering very tight data that you might be using that you expect to have conservation of mass, conservation of energy, then and you're like putting things in tables and checking numbers very carefully, then all of a sudden these, you know, the fact of where you get your values at each one of these locations is all of a sudden going to become much more important to you, because now you're looking for quantitative values. And if you're looking for quantitative values, then of course you're going to want to use the best value, which if you're looking at a face value, you know, on your cell, you're going to want to use the face flow rate that the solver would have used or something very similar to it. So let's just take a quick look here at this kind of visually of where these collocated data are here. And it's kind of the same thing that we saw before. However, each one of these black dots is where our conservation of momentum values are stored. And here, a normal flow rate through each one of these phases. And now, previously when the staggered mesh, we were like, it's close enough. these values for the solver for each one of the faces, this is the precise mass flow rate going through each one of these faces. So there's no approximation there. This is the exact mass flow rate, and it's always the mass flow rate normal to the face. And typically the solver will not really store each velocity component there. Perhaps it may depend on how it was implemented, but typically it's the mass flow rate that's stored there, which implies a velocity given the area and the densities in those locations. So that's the gist of the collocated data and why we went from the staggered mesh, you know, the numerical issues, and how we ended up with this collocated storage method that kind of introduces a velocity field that is scattered not between the cell-centered values, but also values that are on the faces of each cell. So now that we understand the nature of the CFD velocity data provided by collocated algorithms, how do we use these data to perform reliable surface integrals? You know, kind of the topic here. Now that we kind of have a good handle on where the data came from, you know, why it is the way it is, and how do we deal with it at this point? So, but before we do that, maybe we should, what is a surface integral? What does it mean to do a surface integral in general? So maybe I'll do a quick review of that just so we're on the same page, just so like we were on the same page of collocated data. So let's just talk about a surface integral here. We have a surface integral is typically just some weighting method. And here we would like to say we want to find the average value along this surface, this red surface here. So we would basically pick a weighting value and the value for each one of these kind of blue dots that you have right here. So we'll multiply it by the weighting value, the value of our scalar field that we're integrating there, my weighting value. We sum all that up, and then we sum our weights and we divide it, and that gives us a nominal area or average value of some sort right here that conserves or does, you know, this is the average value that we're looking for here. So that's kind of the quick math here. So we're always looking at some sort of faceting, and then we're looking at the centered value in each one of these facetings. So what about this weighting method? What is that W value? How do we choose what it really is? And the weighting method there, it depends. But the thing is just like when you're setting up a problem, like you're doing a homework problem or whatever, you need to pick out, you have to weight your values coming in and out. And depending on if it's a force, perhaps you might use an area. If it's if it's enthalpy, you might use mass. So you need to pick the appropriate weighting method to use to find your average value. And picking a weighting value is, of course, important. And so maybe let's just take a quick look at choosing that value. And the problem I'm going to choose is a relatively simple problem, I think, that we can visually look at here. We just have a T-junction example here where we have flow coming in at the top, it joins and goes right, and then we have flow coming from the left, it comes in and goes to the right. And we're going to do a surface integral at the very end of this. And let's do some very simple calculations here. So here is our problem, and we're going to do an energy balance on that. In this particular case, we'll just say it's standard air. It's coming in hot at the top at 600 K and coming in cold at the bottom at 300 K. We'll say there's no energy loss. The mesh is nice, beautiful, uniform, every cell's the same. And you'll notice in this particular image that I've shown here, it doesn't have the smooth contours. It has each cell is colored by the centered value. I mean, this is the actual data that you have in our CFD simulation. And you can see how it's joining together. And then on the right-hand side, we'll make some assumptions about what enthalpy is, and how do you find mass flow rate? Mass flow rate, through a particular surface is, of course, the density of each surface, the velocity, the normal velocity on that surface, and then the area. And then on the right, we have kind of the nominal values over here of what these would be right here. So we kind of have all of the information we need to come up, and we would like to find what is the average temperature at this location. And we really shouldn't use a CFD simulation to solve this directly, because we could kind of know this in advance. We don't need a CFD simulation to tell us what the average value is here. The CFD simulation tells us these numbers right here, which are far more interesting, and that's what we use a CFD simulation to go down below what we could typically do with a spreadsheet. Our spreadsheet could tell us what it is here. Our spreadsheet can't tell us that it's cooler down here and hotter up here. And that's what we leverage our CFD tools to do, to give us this information that we can use in the future. So we have all of this information here, and let's see what happens here. So how do we find out what the average value, and this is what you would do in a typical spreadsheet. We can look over here, we can find the mass flow rate coming through up here by the density and the velocity and the area, and then our enthalpy coming in here. So we can find out the amount of energy coming in here, and we can do a similar calculation for the left-hand side as it comes in there. And so we know the total mass coming in, or the total energy coming in over here. And then over on the right-hand side, we know the total energy coming in. And so therefore, we know the total energy that must leave over here on the right-hand side. So if we divide that by our known mass flow rate right here, we can find our enthalpy, and then using our simple enthalpy relationship, we can find that the average temperature coming out here has got to be 450 degrees. That means that is the temperature that conserves energy. And this is exactly what we want. So we want our surface integral. If we were to do a surface integral on our surface in our CFD tool, we certainly want to get that number as well. If we don't, then that's going to be really confusing to deal with. So let's do that. So if we go down here and we use the numbers that were shown previously, and we sum up the density time, mass weighting is, I guess I should back up and say, mass weighting is the appropriate way of finding the average temperature in this particular case, which is the density times the velocity times the area times the temperature. We sum all those up and divide, and lo and behold, we get the number we would expect, which is exactly what we want. And so this is kind of our first surface integral of the ending values here. There's no ambiguity about interpolation in this particular case, because it's at the end, and the data is there. We don't have to determine or use any interpolation in this particular case. So we've gotten the value we want, but I think maybe just for example purposes, what would happen if we, for some reason, decided that, the surface area is probably a good way of determining what our weighted value should be. And so we use that same surface integral technique to find our average temperature. And you can see here, if you do that same calculation, you're going to get a number of 475 degrees. And that is quite misleading, because that now defies conservation of energy. And so say, for instance, we had run this simulation and we had gotten an area weighted average at the end, and we hadn't done a spreadsheet analysis, and we did not know that the temperature was supposed to be 450 degrees, and we were doing design work, and our boss told us to get a temperature of 450 degrees out of that. And we did a surface integral and we got 475 degrees. And then we would be tempted to go back and say, well, I need to change the temperature of one of my inlets to a lower number so that I can get my value here. And all of a sudden now you're really in a position of doing something that when you go out in the field and do that, that is physically impossible, and you could really provide some misinformation for designing things. So I hope this is a, a very simple example, but it should really accentuate the importance and the implications of not using the correct integration techniques and how it may impact design decisions in a very negative way. So anyway, that's kind of a very simple example of surface integrals and how you put them together, and why I'm very adamant that they should really represent the data and the methods used within the CFD solver. So what are the lessons learned here? I guess I kind of went over some of these. The importance of using mass flow weighted. When looking at surface integrals, they're really, I guess I kind of hit all of these here, so I'm a little ahead of myself. So now let's look at another example. This one really didn't look at the collocated nature and how to deal with the inside. So I'm going to choose another problem here to look at and say, all right, what happens if we want to look at the inside? And so the problem I'm choosing is a very simple problem as well. And this is, I'm calling it developing viscous slot flow. And so what we have here is we have a slot, and we're gonna, I've looked up the data for flower honey here. And so we're gonna assume that we have a uniform velocity of honey coming in on the left-hand side here. And then as it goes from the right, kind of developing flow, it's of course a very viscous fluid, and so the sides, the velocities begin slowing down near the walls, and then of course the velocity in the interior begins to accelerate. And what we really want to look at here is this I have a magenta surface right here in the middle, and we want to look at an interior surface integral right there. And specifically, we're really just going to kind of focus on how do we come up with a value for this face right here. That's what we're going to really focus on in a very specific way. So let's do that. But first, let's kind of talk about how to deal with this collocated data here. So we're looking around that face that I was just showing you here, that right here, and how the different methods that people use to come up with the data at these locations. And I'm just going to kind of highlight here. So here, these green dots right here represent the cell centroid data for each one of these. And that's the data. That's the CFD data that we have, and that's all we have. And then we're left to interpret that data in some way. Using a program is going to typically use that to extract that data for us in some way. Then we have, and typically what happens is, I'm going to just switch down here. We have these vertices. These are the mesh topology. These are the corners of our mesh. Those are another location that people use to move the data to, so they're more convenient to use and deal with. So that's another location. And then of course the face center is another. This black dot is the center of each face of our mesh topology. That's another location that is very convenient. And of course we need those for our surface integrals. So these are the kind of the three layers of locations that you might want to look at and move around this data. So let's just look at the first one, and that's the face data. And so many people kind of refer to the solver technologies that are used today as face-based solvers. And one of the reasons they refer to that as face-based solvers is the algorithms are really focused on, because they're using control volume methods, they're really kind of interested in what passes through each face of a control volume. And so the algorithms themselves use interpolation techniques that leverage between the data, primarily the data on either side of the face. So you can kind of view it in this particular case, just a simple linear interpolation between here and here gives us a nice value right here. That's the typical way that solver algorithms use to come up with the data right there. And if you're doing anything there, that would be the interpolation technique that maybe you would want to kind of gravitate toward if you're interpreting this data in the best way possible. But when you're using post-processing tools that are kind of ignorant or unaware of the solver algorithms themselves, these tools, they don't really use that information. And usually if you take a collocated solution and you pull it into these tools, the first thing they do is they project the collocated data to the vertices of the mesh. And you can kind of see right here, these yellow lines right here. So for instance, this vertex right here might be some sort of interpolation of these 4 data points that gives us a value right here. And likewise up here, you might do the same thing between these 4 and that value right here. And then once the facet, it has projected the cell-centered data out to the facets, then if you were to ask these tools for integration information, it's going to use this facet information to find the cell centroidal data, which would involve a second interpolation to the centroid of each face. That's generally what many of these tools do to process this data. So let's think about that. So now let's look, and what I want to do here is let's look at these different techniques about what kind of error will be introduced in our prediction. And we're just, what is the velocity right here? And so right over here, I've looked at the velocity in this particular case. And based on the solver itself, if you extract that value at this location, the velocity, implied velocity is this number right here. And I say, well, there's no error here because the solver, this is what the solver thinks. The velocity should be here to conserve mass. But now if we use this neighbor interpolation, kind of the algorithm that the solver would use, just linear interpolation, a very minimal error here. Because it's such a simple case, you're not really going to see an error, but there's a small error. Probably don't even care about it. So that's okay. But if we were to use this vertex interpolation method here, you can see that this is the value of the velocity that you might get there. And now we've actually introduced an error on the order of 20% for this very specific case. So, and that's pretty undesirable. And this is where I was talking about, if you start seeing inconsistent results when you're post-processing things, this is what I'm talking about. And sometimes it's you're just going to have to deal with it and say, okay, this is the way it is. Or if you're using tools such as the GUI that's designed and goes with Azure, then you wouldn't have to necessarily deal with these because Azure would have taken care of the details of getting just the value you wanted at the particular location. So this is the example I have here for just looking at these interpolation techniques, and hopefully this gives us a flavor of how these interpolation techniques are put together and where the data is moved from the cell-centered values out to each one of the vertices. So now we've done this, let's look at something a little bit more complex. And the problem I'm choosing here is let's just say we have our boss has come to us and he has this problem here, and and he has this duct here that has a pleated filter in it, and you can kind of see this magenta pleated filter here. And on the left-hand side, we have a process over here. It's doing, we don't know what, but what happens is that flow comes in here. He's going to tell us that it comes into this duct. It's uniform. Perhaps it probably has particulate in it, for instance, that needs to be removed. But it also comes in with a very significant temperature gradient here, where there's a linear variation of temperature between a low temperature and a high temperature, and he's a little afraid that it's going to burn this filter down here. And so what we're going to do is let's put some mixing baffles in here, these little plates, to try to mix the flow up a little bit and kind of spread out this high temperature variation so that it doesn't burn our filter. But it also says, well, we're putting this flow structure in here. We could get some high velocities, or the flow may not pass through this filter very well. And so he's interested in knowing what is the normal velocity on the entrance of this filter. So we really want to look at the velocity normal just to the entrance of this filter. That is our goal. So that's our surface integral plane, is the surface coming in of this filter. This is the problem that we have set up. And then, I guess, to finish out what happens to the flow structure, it goes down here and then it goes out to inlets. That's the problem that we're going to kind of set up. The air is, this is air that's going to here. And we've perhaps in this particular case, then maybe the fluid properties are temperature dependent. That's less of an importance here. So this is the mesh structure that is chosen here. And you'll notice it's relatively coarse on the left and right, but the filter itself, the pleated filter, is very fine because we're actually resolving the thickness of the filter and putting a resistance in there. So so you can see that the mesh is very dense right there, although it's all hexahedral. So here's kind of a zoomed in view near the filter here. And you can kind of look at the mesh topology here. And I'm kind of highlighted, this is the surface, this magenta. This is the surface we're interested in looking at here. This is where the pleated material is, where our flow has to pass through it. So this is the problem that we're interested in looking at. So here's what the flow field looks like. Just a general get the gist of what's going on here. We can see in the velocity field, the top image is the total velocity field, has a nominal velocity of 5, higher velocities on the order of, 13 or 14, lower velocities, closer to 0 behind the wakes of each one of these. And then the lower one shows the temperature in Kelvin. And this is the gradient in the temperature, and you can kind of see how it does get a little bit more mixed up, and especially the peak temperatures are lowered a little bit as they pass by the mixing baffle. So that's just the gist of what flow structure we're looking at here. So, and now let's look at the flow of the velocity field at a couple of locations very close to the filter. And this is the first one in the pleated filter. This is our pleated filter here, and we're looking at the velocity vectors here. And you can kind of see right here, the entrance, the air is kind of passing right through. Right over here, the air is kind of going tangent to it, but as it gets further and further down, the resistance is high enough that it's just kind of nominally going through here. But then the other side up here on the higher side, you can see that the air has come in here, but it might not be going through the filter in this direction. It might actually be leaving right here. So the flow structure on this surface, not only is the surface very curved, which is kind of challenging to do a surface integral on, or even kind of visually look at. I mean, this really kind of, if you want to know what the, kind of quantify to our boss what the nominal normal velocity is into this filter, it's challenging to do with filled contours and in a quantitative way. Qualitatively, you can kind of look at it, but specifically where, is the flow going through here or not, it's hard to say. Maybe it is, but if we did a surface integral, maybe we would know that if we looked at the details there. Now let's look, now I'm looking kind of in the right-hand side of our pleat. This is where the flow is leaving the pleat. And you can kind of see the same flow structure where the flow is kind of passing through the filter right here, but this is the surface that we're interested in here in our pleated filter. So, and one of the reasons we might want to look at the normal velocity on this pleated filter is the normal velocity. If we have material, say particulate that we're catching on this filter, the areas where the normal velocity is going to be the highest on there is probably where, if the particulate is kind of homogeneously distributed throughout the gas stream that's passing through there, the normal velocity is also going to be the areas where potentially the particulate could build up the quickest on our filter. So this is another kind of motivation for looking at that normal velocity. And then one more location here, we're going to kind of look, this is right up at the very top of the wall here. So this is where the flow is kind of being trapped and our filter kind of joins in with the outer wall here. So you can see how the flow is coming in and then it's kind of expanding through. But this is where we're going to do our surface integral. So this is kind of giving us the gist of, that now we're looking at something not nearly as simple, but we don't really have any data on this surface because these are all interior surfaces. So color contour plots, they really provide very nice qualitative descriptions of the velocities and temperature predictions. But if we really want specific data, we want to know what the high velocity is, the low velocity, the normal velocity, any of these things, or the surface temperatures, these require some sort of interpolation technique that I've talked about before to get the data on this surface. That's really what we are going to be needing to do here. So I've gone through and I've collected the data on these surfaces. And so here is a plot, and there's a lot of stuff here. So let's kind of go over there. What I'm plotting right here on the x-axis right here, this is the normal velocity going into that surface of the filter. And on the left-hand side, this is kind of a cartoon showing the height. So right here is the position from the bottom of the duct to the top of the duct. And you can see here is the pleated filter. And the pink, this magenta line is the collocated. This is the solver's choice about what the normal velocity would be along that surface. And you can kind of see where it is quite irregular. And now you can see right here, anything positive, it means it's going into the filter because of the conventions that I chose in the surface integral. And that means that any negative velocities are velocities that actually are going the opposite direction through. So and remember when we were looking at those velocity fields a moment ago, we were speculating, is it going in or out? And in fact, there are a few locations where it's actually going out. And we were looking at perhaps this one, you can see it's negative right there. So there's a small area where the velocity is kind of negative. So here we've done, this is the type of information that, as a consultant, I do all the time, because this is what you are going to relay to your customers. This is what your customer is truly interested in, because these types of things are what are going to help him understand what he is trying to do and what he may be able to do to solve his problem, is these types of plots. So the question is what kind of errors, if I use other methods of interpolation to look at this data? And so this is kind of the same plot, but what I've done is we have the phase interpolation method, or this, where we use the value on either side of the cell, which is the magenta line, or the vertex interpolation. And this is the error in the velocity. So the nominal velocity that we're expecting on this surface is right around 1 meter per second. And so if we had no air, then all of these lines would be 0. So right over in here. So like near the walls, you can say that the air from the prediction that the solver thinks the normal face velocity should be, as opposed to determining a value using some sort of interpolation technique near the walls, could be 0.4 meters or greater different than the velocity that would be actually there, which is a pretty sizable number if your velocity itself that you're trying to characterize is on the order of 1. So this is essentially like a 40% error. And that would probably be very important to us and not acceptable in many cases. Other areas, like right over in here, these are marginal. You know, that's maybe 10% error, maybe this is 4 or 5%, and maybe that, depending on what I'm looking at and the data that I'm looking at, maybe that would be an acceptable amount of interpolation error, and I would be able to process and evaluate my results using some sort of an interpolation technique with a fair bit of confidence. The problem comes in is if we did some design simulations and say, for instance, we changed our mesh topology and we began comparing our design simulations and trying to ferret out differences on the order of 5%. This is where I'm going to talk about it. You start having the possibility of getting ambiguous results. It's like, I was expecting it to be different, but now what is really the right answer? And so this is the example I have here of doing a surface integral of a much more complex surface. And then kind of trying to characterize the errors that you might actually see if you could kind of roll back and look underneath the hood as see what the errors really are. So now, and we can also look at the temperature here. And then in this particular case, temperature in this case, you're not going to really see any differences here. And the differences between face interpolation and vertex interpolation is not very different in this particular case. But you can see that the temperature variation along this surface does have a fair bit of variability, which is another thing that we may have been wanting to look at, like say, for instance, is it below? Like if you look over on there, you were looking at a maximum temperature and say, for instance, if the temperature was supposed to be below 850, that our filter material wouldn't be damaged, we'd be fine. If it was 750, then we would know that this area of the filter right here is going to be a potentially an area where the filter could be damaged by higher temperatures. So that kind of characterizes that, but the next thing that we're really running out of time here, but I would really like to discuss this. Right now, the examples that I've chosen are based on these 2D meshes, which are of like superb quality in terms of mesh quality. And of course, the higher the mesh quality, the better your solution fidelity, the better you can post-process these things. But the simple fact of the matter is that when you do industrial problems, you're going to go to 3D, and 3D, once you move to 3D, the mesh quality and the ability to get very high quality meshes degrades rapidly. And also, when your meshes degrade, then your ability to do surface integrals also degrades, because the data is all of a sudden becomes even more complex. And I thought before we end this, it's worth discussing that and maybe looking at one more problem here and revisiting that slot example and looking at some of the implications of if our mesh quality is not ideal, what kinds of errors and why are those errors occurring? So the one I chose is the slot example. And if you remember before when we did this slot example, it had a very pristine mesh. And what I did is I just took the same exact mesh topology and I just distorted it. And you have so basically some distortion, but the exact location right here of what we're going to look at remains the same. And just out of comment, you can kind of see here, we distorted the mesh, and you can see immediately how the solution itself, it's the same setup and everything. You can see how just this distorted mesh here, because of false diffusion, has really had a significant impact on our prediction itself, where it basically, even though you would expect that high velocity to kind of pass right through this area, because of the mesh structure, it essentially acts as a mixer there, which is completely numerical, not physical at all. So let's just flip through here and look at where our data is. And now our data is a little bit more complicated here, because now the cell centers, especially for this cell right here, we're not drawing a straight line from left to right. The line kind of passes from up here to down here, and as well as like finding these vertices values right here. And so now if we go back and look at so the solver in this particular case says that the mass flow rate at this particular location should be, on the order of 5.3, which is zero error. But now in the previous one, when we did our neighbor interpolation, it was very precise. But now we've introduced all of these other complexities of the lower mesh quality, and now we've introduced a 3% error, almost 4% error, just for our neighbor interpolation. However, our vertex interpolation became much lower. And why would that be? Well, the problem is that the stratification here, because it essentially acted as a mixer, the stratifications became much lower. And so now the error is much lower because there's not as strong a gradient. So this is just a quick example of, we don't really have time to look at, the complexities of 3D, but 3D models are going to suffer more significantly when you do your surface integrals because of just this issue that I'm pointing out right here. So then the last thing I want to talk about is, and we didn't really talk about it at all, there are a couple of different facetings that are used and very widely used. I've talked about a faceting that is always a subset of the mesh topology. But in general, with your post-processing and you would typically put these domain cut facetings through here. So where you would essentially cut through your domain, and then you get a resulting faceting here, which is on the left. So here in this particular case, you have 1, 2, 3, 4, 5, 6. And so now, as you can imagine, like we were talking about, if we were going to do a surface integral on this, and we wanted to get reliable information, it's now even another layer away from the CFD data, and it's even going to be more difficult to get information that is reliable and faithful to what the CFD solver itself has done. And so I say right down here, if you know that you're going to be interested in surface integrals of some sort within your domain, it is really in your best interest to try and choose your mesh topology with the facets that you intend to do the surface integrals on embedded in your mesh. That's where you're going to get that's where you have the best opportunity, is at the meshing stage, to get the best surface integrals when you go to the post-processing stage. And so this is just a quick comment about, these are ways of setting up your model so that you can really get good surface integrals, and reserve the domain cutting ones that you use for post-processing of filled contours. Of course, those are very handy to do there. And those also allow you a greater flexibility. You don't have to make as many decisions up front, but that's it. So anyway, that's the last comment I have there on surface integrals. So it's like, just to kind of summarize here, collocated control volume algorithms, they really provide us some really precise definitions of momentum at all cell centroids. provides this precise information at the centroids of each face. It's generally a better spatial representation of the fluid velocity field for complex geometries. Surface integrals of CFD data, they provide access to averaging surface integral for engineering analysis. That's really where the value comes from CFD tools, is to be able to use a CFD tool to solve a problem that you can actually build or do something with. That's where, you know, you're actually doing something. And then the other thing is, it's like many normal, this topic right here, many area or surface integrals require a mass flow rate averaged value. And so if you're doing any surface integral type thing like temperature, you want to make sure that you use the mass flow rates of the faces that the solver has generated, if at all possible. So that being said, post-processing tools that are aware of collocated CFD data are very desirable to use. And of course, Azor leverages these. I have spent, hopefully you can see, I've spent a lot of time thinking about this and putting together these over the decades, making sure, getting values that I didn't understand, and making sure that, you know, I always want something that is faithful to the solver algorithms when I'm post-processing my tools. And Azor's tools are very keen on doing just that. And the generic post-processing tools, and I'm kind of singling out ParaView here, but there are many of them out there. Typically, they don't access that data, or if you are, you maybe have very complex scripts within ParaView, because that is a very powerful tool, and there are many tools that may provide that, but not easily done. So that's where I'm talking about these specialized scripts. So anyway, that kind of concludes the discussion I wanted to put together today. This, of course, is based on all of the work that I've done within Azor, and Azor is a kind of a commercially available tool that is available if you guys might be interested in it. And you can see the website down here at www.azorcfd.com. You can get a free trial. But I guess maybe we'll just open it up for questions if there is time at this point.
Thank you, Jeff, for the wonderful session. It was very, very useful, especially for students as well as those who are working in the industry. And these are the typical questions people have, like, why should I take averaging? Which type of averaging I need to take? Is it surface? I mean, area weighted averaging or mass weighted averaging? And yeah, so I mean, I have seen I have faced these difficulties in the past as well, working in the industry. So we have few questions. So Zing got one question, like, it's a bit confusing. Why don't use solver values on surface? Why to interpolate?
Solver values on surfaces. Well, the solver itself only has values at the centroid of each cell. That's where the solver actually has data. So if you imagine, if you were collecting data with a probe, you only get it at a particular location, and you maybe want to pick a couple of locations where you have collected data, but you want to speculate what it is away from the locations where you collected data. You're probably going to, the only technique you have is to use interpolation. And that's what you have. When you do a surface integral, you are using something that is not through the centroid of each cell. I suppose if you wanted to choose a cut through a particular cell, which is a lot more challenging to do, then that doesn't really represent conservation of mass. So like if you say, for instance, cut through the middle of a cell, and you're right at the centroid of that cell, that's a momentum conserving velocity, not the mass conserving velocity. I could maybe let me flip through here. So let's say, for instance, if you can see so like say, for instance, you put a post-processing plane right here, and then you had you said, okay, I know the precise value right here. The momentum is only conserved right here. So in more complex situations, that not, if even though you kind of could project and know the area right here, that doesn't necessarily mean that that average value that you have right here projected on a surface through here is going to conserve mass. The only place that's going to conserve mass is right here on this, because that's what the solver has enforced. Hopefully that answers his question.
Yep. Thank you. There's a question from Asif. In the case of 3D complex geometry, it is very difficult to choose a mesh topological surface because unstructured mesh for internal, internal use. Is there any suggestion for that?
Well, I guess it depends on the mesh generator that you use. Because it depends on the mesh generator you use. The mesh generators that I use allow you to have surfaces inside that the mesh itself snaps to. So it really depends on the meshing tool that you're using.
Got it. Thank you. And there is one question by Subhasish. So, there were other questions by other students who filled the registration form. Very similar question. For which physical quantities should we use area weighted average? And I would extend it, or on which quantities would you prefer mass weighted average in general in CFD?
So that is a tricky question, and I can certainly give examples. Like, say, for instance, pressure on the outside surface is going to be area weighted because it's force. And if the temperature, since it's a transported field and you basically have a physical object that's crossing a barrier that has mass, and that is mass weighted. So temperature is a good one that is mass weighted. If you have a mass fraction field, it's going to be mass weighted, but it really should stem back to what you're looking at. And for me to definitively list out every single one of them is very challenging. And there may be cases where you might want to use area weighted for one in one situation, or a mass weighted in another situation, depending on what you're trying to conserve. So that's why I'm saying you really want to know the conservation methods that you're using. And then that should just obviously point to the weighting method that you should use.
Thank you. There is a question by Adiraj. Would you say that CFD solvers that often runtime post-processing would be preferable to opening the data in a standalone post-processor and creating integral or plots? So I'm not very clear what exactly meant, but maybe you can also go through
Well, yeah, well, I know that like some tools, there are two different ways of post-processing. There are maybe rudimentary tools that allow you to access some CFD data, but then they might have a separate post-processing tool that you can pull things into and then post-process them there. And it really depends on the implementation of them and how that post-processing tool interprets the CFD data, kind of how I had outlined it there. And that's one of the things that Azor does is Azor, the solver itself runs and it stores all of the data. And then when Azor reads it reads in the phase flows, it reads in the self-centered data. And then when a surface integral is done, it has that data available to do surface integrals. And so you're looking for, I mean, I'm just talking about Azor in particular because that's the way it was designed. And other tools, I'm sure, offer similar ones. I know, like, for instance, ANSYS Fluent, you have to use special menus if you want to use the phase flow information in order to get the correct values. So, and they have special menus. So you have to kind of navigate those systems. And
Yeah,
mostly what I'm saying is that, like, when you're looking at these tools and you start seeing inconsistent values, hopefully this discussion will help you understand, oh, this is probably why I'm seeing. So, and then you'll especially see these things, like if you were looking at an area where the velocity gradients are very strong and your mesh density is fairly coarse and the quality is really low, and all of a sudden you're not seeing mass balance or momentum balance or energy balance, then those are likely indications that the post-processing tool are not doing a fair job of interpreting the CFD data.
Perfect. Yeah, and Jeff, just to extend that question, you mentioned like Fluent, there are additional post-processing tool like CFD Post. So to extend it to connect it to Azure, can we import Fluent data to Azure and do the post-processing?
Yeah, Azure has the ability to pull in the data from Fluent, but it doesn't pull in all of the face flow data.
Okay.
It pulls in the interpolation data. So if you write out an IP file from Fluent, it can be read into Azure. The problem is that the face flow data is very specific to numerical algorithms. So even if Azure read it, it might not be particularly faithful to the algorithms that ANSYS uses, because obviously they're different software packages.
Yeah. Good. And there is a good question from Maria. In finite volume method in physics, whereas source term of velocity is applied to the center of the cells, how can we aware of a decoupling issue between pressure and velocity if happens? How does it look like, or is it only a matter of simulation stability? Does make the difference in the momentum equation to apply source terms in cell center than on the vertex of the mesh? So maybe you can also go through the question there. It's a long one.
Yeah, well, so typically algorithms are written, their control volume algorithms depend on the fact that you are solving something at the centroid of each cell. There are algorithms like CFX that are vertex based, where the control volume itself is kind of formed around the vertices of each cell. But in general, any source term in terms of the discretization and the control volume techniques is always applied at the centroid of each cell, whether the centroid is formed around the vertex or whether the centroid is at, the centroid of the topology that you're using.
Thank you. There's a question by Fee. I see Azure CFD can visualize simulated results by itself. What is the backend engine for the visualization part? Do you integrate OpenGL in your post-processing tools?
Yeah, Azure is actually kind of because I wrote Azure as the post-processing tool before any post-processing tools or before ParaView was, or even the VTK toolkit was a thing. So Azure is built on the foundations of OpenGL itself. And all of the faceting and the rendering and everything is basically very foundational OpenGL tools. So there is no sub library. It's not part of ParaView or any other post-processing tool. It's all foundational C++ code that I wrote years ago and have continued to write to post-process and render and show these the views. And then if you're interested in what Azure's GUI looks like and stuff like that, there are lots of YouTube videos and the likes at the Azure's CFD website.
There's there's one question. Can we take advantage of AI techniques for mesh generation and topology in this CFD software?
So that is an interesting. So I've worked with a number of different people for AI, but mostly the AI things that I have done is for training the AI. So I've worked with people who want to use Azure and they want to run hundreds or thousands of simulations, simulation variations, and Azure itself. There's kind of two sets. Azure is basically just a simple program. It has no OpenGL part of it. the solver engine itself, so it can be run from the command line very easily. And so it's very easy to put it in scripts to run hundreds or thousands or millions of CFD simulations if you would like. So that from that perspective, it could be possibly used for AI. There is a strong scripting language within the Azure GUI that's based on JavaScript. So if you wanted to, say, for instance, mine data to train or do things based on AI, I suppose there's a possibility there, but I have never explored anything like that.
Thank you. So a couple of more questions, and maybe we can close that our meeting. How would you suggest start developing a program in C++ in context of CFD as a beginner? Which problem shall we start with?
Well, I'd say probably the square lid-driven cavity is the classic problem to start with. The mesh topology is simple. There is lots of data out there, and there are a lot of examples of how to do that. So I would probably start with that problem. And it seems like a simple problem, but I'll say I solved that problem originally, probably 25 years ago, and it took some time.
The mass flux errors becomes nearly zero easily, but for energy flux, it is difficult to achieve zero error for industry level problems with maybe 5 to 15 million cells. If we increase the cells, the computation cost increases. What percentage error of energy flux is acceptable for industry level problems?
All right. Of course, that depends on the problem and the amount of energy going in and out of your, the complexity of your energy problem itself. One of the things that I would suggest is that you kind of scale and look at if you have an energy balance and try to put that in perspective to what you might be looking at. It's like, say, for instance, you had an energy balance of, I'll just say 20 joules. So you say, okay, I have 20 joules of unknown in my domain in this particular area. And then you would look at your temperature in that area and say, how much would this change my temperature in this area if I took away or added that amount of loss? And is that important to me? Is one way of kind of scaling and looking at a problem in that way.
Okay, I think I think that's it. I think and really thank you for extending the talk. We planned only for 1 hour, but it got a bit extended. So thank you very much, Dr. Jeff, for your time and collaborating with us. And hopefully we will have a lot more to do together. And yeah, we'll also encourage our students to try to use Azure as a tool for a trial version and see how they can learn from this.
Yeah. We have a lot of tutorials, and for students, we have special options for students too that people might want to try to take advantage of. So
thank you, and so have a great day for you.
okay, you too, and it's a pleasure being here, and thanks for letting me talk about CFD, which I love to do.
Yeah. Thank you. Yeah.
All right. Bye.
Thank you. Bye.